Now we shall prove the fundamental theorem of arithmetic. The theorem states that every integer can be factored into primes. So we know this, and we actually use this result in high school mathematics. So every integer can be factored, or can be it is either a prime or a product of primes, and this representation is unique apart from the order in which the factors occur. So for example, if you consider say this integer 17, then 17 is itself a prime. So therefore we can consider 17 is equal to 7. That is the prime factorization of representation of prime number. It is either prime, or now if you consider another number, that is 60. Now this integer is not a prime, but it can be factored into primes, or it can be written as products of primes. And we know how to express this as, so this is 2 into 30, and then again this 30 is not a prime, then again it can be factored, and we can write that as 2 into 15, and then this is 15 is not a prime, so it can be further factored as 3 into 5. So thus this is a composite number, and that is written as product of primes, and this representation is unique. So there are no other primes except these two, repeated 2 times, 3 and 5 as the product of 60. So 60 can be written only in terms of these primes as product, and that is the meaning here. The representation is unique. So we shall now consider the proof of this theorem. Suppose n is prime. If n is greater than 1, positive integer greater than 1 we have to consider. If n is prime, there is nothing to do. Just like this, 17 is prime, so 17 is equal to 17, written in terms of prime factor. But if n is not prime, if n is a composite number, then it has divisors d. So d between 1 and n. 1 is less than d is less than n, and d divides n. So this is the difference between prime and composite number. Prime has no divisor except one and the same number, but every composite number has divisors. For example, if you consider this 60, then the divisors of 60 are, we know, are 2, 3, then 5, further is 10, 6 is also there, 6, 10, 12, 15, 30 and 60. So many divisors are there of 60, and each number divides this. So therefore 1 between d between 1 and n, and d divides n. So now we can consider this in these divisors. These are the divisors of 60, and we have to select the smallest of these. So we select a smallest divisor of these. Among these, and say P1, or P1 is the smallest divisor of among these divisors. Then we can write n as say P1 into another number n1. So if then we we claim that P1 is a prime. If P1 is not prime, now you can observe here, 60 is the number, these are the divisors of 60. And now you may see what is the smallest divisor of 60, positive divisor of 60. And that we are arranged in increasing order, so therefore this is the smallest. So this is the well ordering principle. We can order the numbers, positive integers, and we can select the smallest of this. And suppose that that is P1, and we now claim that P1 is prime. This 2 is a prime number. If P1 is not prime, then it has a divisor Q. Then there exists a divisor of Q of P1. One less than Q is less than P1, and Q divides P1. Now you see we have Q divides P1. And that P1 divides N. P1 we have considered smallest divisor among these as P1. So the smallest divisor of N is supposed to be P1. So Q divides P1 and P1 divides N. So this implies, by theorem in our earlier chapter, Q divides N. A divides B, B divides C, A divides C. So Q divides N. And Q divides N means what? Q is a divisor of N. And we have written Q is smaller than P1. So this is a contradiction, because P1 is the smallest. Smallest divisor of N is P1. And Q is a divisor of N which is smaller than P1. So that is a contradiction. Contradiction to our choice of P1. So this is a contradiction. To our choice as choice of P1 as the smallest positive divisor. Of N. And thus this P1 must be prime. So we have to claim like this: if P1 is not prime, we get a contradiction, and this proves P1 is prime. Hence P1 is prime. Now P1 is divisor of N, so therefore we can write N as P1 into N1. Now let N is equal to P1 into N1. Now, what is the meaning of this is, we have considered the example of say 60. 60 we have written as 2 into 30. And you may see this means P1 into N1. So first factors we are considering for N. P1 into N1. If N1 is, and this N1 will be less than N. If N1 is prime, then we get the representation like this. So product of primes. Then N is, P1 is prime, N1 is prime, that is N is product of primes. So this proves the theorem. Then we get the result. The result of the theorem. Now further, if N1 is not prime, Then, as in the first case, see n we have written as P1 N1, then we can write, then there is P2 divisor of prime divisor of this N1. N1 such that N1 can be written as P2 into N2, and this N2 is less than N1. Now you may refer this. So first we have considered 60 as an example. We can consider 60 is 2 into 30, that is P1 into N1. Now what is N1 is 30, it is not prime, so it can be further factored as 2 into 2 into 15, and this we have considered as P2 and N. So here it is repeated, but sometimes it may be different. They may be equal or may not be equal or different. So thus this is now written as P1 and this is P2 and this is N. So thus N1 is written as P2 into N2, and therefore we have N is equal to first representation of N is P1 N1, and now what is N1? N1 is P2 N2. So P1 P2 N, and the inequality for N2 is 1 is less than N2 is less than N. So thus we get the representation for N. And now if N2 is prime, we stop, because what we have is P1 is prime, P2 is prime. If N2 is prime, we stop, because we continue this up to when we get the prime factors, product of primes. So if N2 is prime, we stop, and if N2 is not prime, then we will continue, and again factor N2 as P3 into N3. If N3 is not prime or composite, then N2 is equal to P3 N, and therefore N will be, now the expression for N will be, we have, see N is P1 P2, and what is N2? N2 is P3 N, where this N3 is less than N2, and so on. So this process continues. We continue like this in factoring the numbers. So, but this must stop, because N is finite, and every time we get smaller and smaller factors. Therefore, this process stops. This process of factoring stops after few steps, after some steps. Say k minus 1 steps. Suppose it stops k minus 1 steps. Then what will be the expression, final expression for N? The expression for N will be, then we have N is equal to P1 P2. So this is the first step. N is P1 N1, that is the first step. In first step there are two factors. So therefore in k minus 1 steps there will be exactly k factors, and thus this will be P1 P2 and so on. The last is P. and thus this is the expression, prime representation of n in terms of P1, P2, Pk. And we have considered an example that 60, so 60 finally can be expressed as see, this is 2 into 3 into 5, 2 into 2, 2 repeated 2 times, 3 into 5. So that is the final expression. This is P1, P2, P3, P4. P1, P2 are equal. That is the meaning of the theorem. Every integer is greater than 1 is either a prime itself. If it is prime, there is no need to consider next procedure. But if it is not prime, then it can be factored into primes. And now this is the expression required. So this is the representation of n. N as product of primes. Now this doesn't complete the proof. What we have to further prove is this representation is unique. This is unique apart from the order in which the factors occur. So meaning is the factors must be the same, not the order. So that means this can be written as say 2 into 3 into 2 into 5. But these are not different. Here order is different, but the factors primes are the same. So that is the meaning. So these primes are unique. That we have to prove. Uniqueness. Now second part is uniqueness of this representation. And to prove uniqueness, we shall suppose n has two representations in terms of p and in terms of q. Suppose n has n is equal to we will consider this as p1 p2 up to say pr. Here we have considered pk, here we are considering pr, some factors, and again this can be expressed as in another primes q1, q2 and so on up to qs. Here r is less than or equal to s. May be different. These are different primes than these. So that is the meaning. It has two representations where the primes are different. Where pi means p1 to pi and qj, these are suffixes, are primes. We shall suppose this statement as one. Now what we have to prove, this representation is unique means these primes are also the same, that we have to prove. Now from first what we can say is this P1 divides Q1 Q2 right side. From 1 P1 divides Q1 Q2 and so on up to Qs. This is a factor. P1 is a factor of this right side, and that means P1 divides the right side. And all are primes, Pi and Qj, all P1, Q1 etc. are primes. And we apply now the second corollary of just we have proved last time, as if these are primes, then this P1 must be equal to one of these factors. Then by corollary 2, this implies P1 is equal to Qk for some k. 1 less than or equal to k is less than or equal to s. And now what one assumption we shall consider here is these are orders. P1, P2, PR and Q1, Q2, QS are ordered in say increasing order. So here we shall add this R primes such that, or also we shall assume that P1 is less than or equal to P2 is less than or equal to PR, and Q1 is less than or equal to Q2 is less than or equal to QS. So earlier you may consider this as say 12. Now what are the prime factors of 12? These are 2 into 3 into 2. But we should write it in terms of increasing order. That we should consider this as 2 into 2 into 3. That is the mean. P1 is less than P2 is less than or equal. So here P1 equal to P2, but P2 is less than P3. So similarly here Q1 is less than or equal to Q2 and so on, that is less than QS. Now what this shows, P1 is equal to QK and P1 divides P1 divides Q1 Q2 up to QS, and thus P1 must be equal to Q1. So this implies that P1 is equal to Q1, because for Q2 etc. up to QS these are greater, Q2 is greater than Q1 and so on. So therefore this P1 must be equal to Q1. So this implies P1 is equal to Q1, because this Q1 is the smallest of these, and therefore P1 divides Q1, Q2 etc. implies P1 is equal to Q1. In the similar way, we can prove, or we have Q1 is equal to Q1 is equal to P1, or that means Q1 divides P1. So therefore these will be, we will consider this as P1 is equal to Q1, and before that will divide, P1 divides Q1 and Q1 also divides P1, then this will become equal. So here we may make the correction. So this implies P1 divides Q1. P1 is equal to Qk, and P1 must be equal to the first member, because the other are greater than or equal to Q1, and therefore P1 divides Q1. And in the same way we can prove that Q1 divides P1 by interchanging these sides. Now if you consider Q1, Q2 etc. on this side and P1, P2 on that side, we can say Q1 divides this product. And similarly, interchanging the sides, we can say Q1 divides P1. And if they divide each other, then they must be equal, because these are greater than 1. So this implies P1 is equal to Q1. And thus we have the first on the left side expression is equal to the first factor on the right side expression. And from 1 we can cancel this factor and write the representation. So therefore from first relation or equation 1, we have cancelling P1 and Q1 from both sides because they are equal. So we have P1 is cancelled, P2, P3 up to PR is equal to Q2, Q3 up to QS. And now we repeat the same procedure. So that means now we can say P2 divides this product, and then we can say P2 divides Q2 like this, and also similarly Q2 divides P2, and therefore P2 must be equal to Q2. So repeating the same, the step, we get P2 is equal to Q2, and therefore P3 now into P4. P2 and Q2 are cancelled. P3, P4, next is P4 and last is PR is equal to, here Q2 is cancelled with P2 and remaining are Q3, the next will be Q4 up to QS. So we get this and we continue like this, and if R is less than S, we have written either less or equal to S. If R is less than S, then continuing this process, if R is less than S, we get, now this R factors on left side will be cancelled with R factors on right side, because each factors are equal corresponding. P3 is equal to Q3, P4 is equal to Q4 and so on. So if all the R factors are cancelled, what will remain on left side is 1, and on right side this R is less than S, so therefore R plus 1 to S factors will remain, and that means the remaining will be QR plus 1. QR factors are cancelled up to QR, then remaining are QR plus 1, QR plus 2 and last is QS. So you should know this, verify this. So R factors cancelled, 1 remains, but the S is greater than R, so R plus 1 to QS will remain on the right side. And now this is a contradiction, or this is absurd. Absurd or wrong. This result is wrong. Why? Because Qj are primes and these are greater than 1. Every Qj are primes, here we have mentioned, and therefore this right side product, each factor is greater than 1, and the product of greater than 1 integer cannot be equal to 1 since Qj are prime. And therefore we must have R is not less than S. If R is not less than S, then we must have R equal to S. So this implies R is equal to S. And now you see, if R is equal to S means number of factors on left side is same as the number of factors on right side. And also we have P1 is equal to Q1, here it is. P2 is equal to Q2, and so on, and PR is equal to QR, and R and S is the same. So that means P1 is equal to Q1, P2 is equal to Q2, and PR last is equal to QR. R is equal to S. So that means each prime on left expression representation and right representation are the same. So this shows that the representation of M in 1 is unique. The two representations are one and the same, is unique, and this completes the proof. So this is the proof of the fundamental theorem of arithmetic. So the proof is somewhat lengthy. It is a procedure used, but the meaning is simple. Every integer is factored into primes. So go through the proof and try to understand the proof. The next part we shall continue next time. Thank you.